In this video, we'll be discussing properties of logarithms and using some of those properties to expand and combine logarithms. Our first property says that log base b of 1 equals 0. We'll use our knowledge of exponents to help us understand why we have this property. If we rewrite this in exponential form, this is the same as b to the 0 power equals 1. And we know that anything raised to the 0 power is equal to 1 from our exponent rules. Our next property, log base b of b equals 1. Again, I'm going to rewrite this in exponential form. This will be b to the first is equal to b, and we know that to be a true statement. The next two properties are inverse properties. Recall that when you have the square root of x and you square it, the square and the square root cancel out, leaving you with just x. Similarly, if you have x squared and take the square root of that, again, the square and square root cancel out, leaving us with just x. Properties 3 and 4 are very similar to that. Log base b and exponential base b are inverses of each other. Therefore, they cancel each other out, leaving us with just x. And just as it didn't matter which was on the inside, the x squared or the square root of x, when you did the inverse operation, they canceled out and left you with just x. Well, that's what we see happening in property 4. The next three properties are the ones that we're going to use to combine or separate logarithmic expressions. Property number 5 says if you have a product inside the argument of your log, so log base b of m times n, this can be rewritten as log base b of m plus log base b of n. I again draw on my knowledge of exponents to help me remember this property. If you're multiplying something like x squared times x to the third, we end up adding our exponents and getting x to the fifth. So I use that to help me remember rule number 5, that when there's a product in the argument of my log, I'm going to add them just like I did when I multiplied with my exponent rules. Property 6 says log base b of m divided by n equals log base b of m minus log base b of n. Going back to my exponent rules, if we had x to the fifth divided by x to the second, here we subtract our exponents to give us x to the third. So I remember when I have division in my argument, I'm going to subtract. And our last property addresses when we have an exponent inside our argument. Log base b of m raised to the p power. This p comes out and becomes a coefficient. We get p times log base b of m. Tying it to my knowledge of exponents, when we have a power raised up to a power, we multiply those exponents. So let's use these last three properties to expand and combine logs. Please note that the common log and the natural log are just special case logs, so all of the properties we discuss apply to them as well. So let's write these logarithmic expressions as the sum or difference of simpler logs. When they say simpler logs, they mean that there's less stuff in the argument. Sometimes your answer ends up looking more complicated than the original problem. So our first example, log base b of x to the fourth times the cube root of y. We see that we have a product here. We're going to start by breaking this product up into the sum of two logs, log base b of x to the fourth plus log base b of the cube root of y. I see in my first log that we've created that I have an exponent of 4. Well, this exponent for our seventh property is going to become a coefficient. We get 4 times log base b of x. Addressing the second log that we have, right now I don't see an exponent, but remember that the cube root of y is the same as y to the 1/3. So we can take that 1/3, put it as a coefficient. We get a final answer of 4 log base b of x plus 1/3 log base b of y. Next we have log base 10, so there's our common log, of a to the 4th divided by b to the 5th. Since there's a quotient in our argument, we'll rewrite this as subtraction, log of a to the 4th minus log of b to the 5th. Both of our arguments have exponents, so both of them will come out in front as coefficients. We get 4 times log of a minus 5 times log of b. In our next examples, we're going to go the opposite direction. We're going to take the sum and difference of some logs and write them as a single log. Then we'll simplify the arguments if possible. Now you can only combine logs that are of the same base. So let's write 2 natural log of x plus 3 natural log of y as a single log. Since we're going the opposite direction, we're actually going to apply our properties in the opposite order to combine. When rewriting as a single log, the first thing you want to do is take any coefficients and put them into the argument as exponents. We get the natural log of x squared plus the natural log of y to the 3rd. We have these two logs that we're adding together. We can combine logs by multiplying their arguments. We get a final answer of natural log of x squared times y to the 3rd. You want to check to see if your argument can be simplified. In this case, it couldn't. Next, let's combine 1/2 log of a minus 3 log of b. Again, we'll start by taking our coefficients and making them exponents on our arguments. We get log of a to the 1/2, and you could write that the square root of a if you like, minus log of b to the 3rd. Now we see that we are subtracting 2 logs. We can combine this to a single log by dividing the arguments. We get log of a to the 1/2 over b to the 3rd, and then we check to see if we can simplify the argument. We can't, so this is our final answer. In our next example here, we see that we have both addition and subtraction. We start by making any coefficients exponents on the argument. Our first term turns into log base 2 of x squared. But now we're putting an exponent of 2 on our argument of y to the 3rd. We are putting that exponent of 2 on the whole argument. So 3y to the 2nd in parentheses. This means we have to apply that square to both the 3 and the y. This gives us log base 2 of 9y squared. Our next term we see that we have more than one factor again in our argument. Putting that exponent of 3 on the argument, it needs to go to the whole thing in parentheses. And that outer exponent needs to be applied to the x, the y, and the z. This gives us log base 2 of x to the third, y to the third, z to the third. Now we want to combine the addition and subtraction. You could do this just 2 at a time, but I actually think it's easier to just put them all together at once. They're all log base 2, so I know this is going to combine to be a log base 2. Since I see both addition and subtraction between my terms, I know that this is going to involve both multiplication and division, so I'm going to have a fraction in my argument. Any term that's positive, so if it's a positive log, that argument goes in the numerator. If there's a minus in front of the log, that argument's going to go in the denominator. So our first term is a positive log base 2 of x squared, so its argument x squared goes in the numerator. Our next term is minus log base 2 of 9y squared. Since we had a minus in front, its argument goes in the denominator. Our next term, plus log base 2 of x to the third, y to the third, z to the third. Since that log is positive, its argument goes in the numerator. Now we want to look at our argument and see if we can simplify. Notice that we have x's on the same side of the fraction. We can combine those by adding our exponents. Also notice that we have y's on the opposite side of our fraction. We can combine those by subtracting our exponents. This is going to give us log base 2 of x to the fifth, y to the first, z to the third over 9.